All right, Algebra 2 people. We are getting ready to embark on the last arc of lessons. We've got 4 more to go over, and they're all very, very much related. So make sure you have a solid understanding of each one before you progress to the next one, because they're going to start building upon each other. Okay? It's all about asymptotes, which we saw in Desmos, and wholes, which we also saw in Desmos, but we didn't really explain a whole lot in that Desmos activity. The asymptotes, yes, those were the big canyons with Gandalf saying you cannot pass. The wholes, those were places where things just disappeared, but they didn't look like they should disappear. It looked like a continuous line, but things still disappeared. So before we get into that, we're going to talk about something called excluded values. It is very much related to the domain that we studied last semester and a little bit this semester. Okay, so we're going to refresh your memories a little bit by using an example from last semester. So yes, it was a while ago. So first of all, the domain is what x can be. It's also what x cannot be. Okay, but it's all the things that x can be. For most linear functions and for all linear and exponential functions, x can be pretty much anything it wants to be. It can be just about anything. However, there were some functions that we ran into where that's actually not the case. Okay, so for example, radical functions. If they have an even root, and this is where we did the opposite from inside and the normal part, because y does actually equal positive 2, but x had to do the opposite. So at 3, 2, the coordinates, that's where the start was. And think of, this is the opposite of x squared, that's a parabola, this is that inverse. So it's a sideways parabola, except it's not the full parabola. It only goes up in the positive directions, positive y, positive x. So the domain for this would be all the things x can't be. X cannot exist any lower than a positive 3. So we did this in what's called interval form. So we said, well, it can start at 3, and it can go out to infinity, and it can be anything in between 3 and infinity, but it couldn't be a 2, it couldn't be a 1, it couldn't be a 0, it couldn't be any of the negatives, any of the decimals there. That's the domain. Okay, so it tells you what x can be, and from that you can kind of get what x cannot be. So remember, that's the domain. There are sometimes, for some functions, limits on what you can plug in for x. So that's a domain. For our rational functions, domain is going to come into it again, and we call this kind of domain excluded values. Okay? So I'm going to do a quick sketch of one of the simplest rational functions, which is just 1 over x. And this is not going to be super accurate because it's a quick sketch, but it will hopefully get the idea across. Okay, the curvy lines are all part of the same graph. That's all 1 over x. Okay, and it can go forever and ever and ever and ever until it hits the middle, the origin area, where part of it goes really far down and the other part goes really far up, and they never meet. So it goes up forever and ever, and it can go down for ever and ever and ever, but what's going to happen at 0? They're certainly not going to meet if they're going different directions. And the reason that's happening is because we have 1 over 0 at the origin, and you can't do that. In fact, if you were to put that into your calculator, it would give you something called a domain error oftentimes, your more sophisticated calculators. And that's because you put in something that x can't be. You messed up the domain. That's called an asymptote. Okay? The lines of the function can approach where x equals 0, but they can't actually get there. So they can approach it, but they're going to veer off. So x cannot equal, that's what the equal sign with the slash means, it can't equal 0. Your entire denominator cannot be 0. Okay? So to put that another way, in symbolic terms, we'll actually write out denominator, but then there's that does not equal 0. And that is what is known as an excluded value. Okay? It's part of the domain. It's just a different way of looking at the domain. Rather than saying, oh, x can be all this stuff, we're going to simplify it and say, yeah, x can't be this. All right, so how do we find excluded values? First of all, it helps to know where you're looking. You're going to look at the denominator, and you're going to look at all the variables in the denominator. I wrote in it, but the variables in the denominator, not the numerator. And to make this even simpler, we're going to simplify the denominator. Eventually, we'll also simplify the numerator. And we do that by looking for things like greatest common factor. What is something everybody's got in common that we can pull out? And then if we have something like an x squared value that doesn't go away with the greatest common factor, can we factor it into two parentheses? So that's, again, that's usually when there's a variable squared running around. Okay? Not always, but usually. All right, so let's try it out. We're going to look at the denominator. Now, keep in mind, that's a group. Okay, that's one big group. There also happens to be a group on top, but we're not looking on top right now. We're just looking at the denominator, the bottom. Okay, we're looking for excluded values, and they come from the denominator. And because that's a group, we have to look at the whole thing, not just the k part, all of it. Okay, groups go together, cancel together, eat together, live together. It's like a crazy college dorm. Okay, so what could make the entire group 0? Well, we can subtract over the 9, and we can say, oh, hey, if I plug a -9 in for k, that's what will make the denominator 0. That is my excluded value. Now, kind of like the -3 turning into a +3 here on the graph, you can do the same thing with this. You can say, oh, +9, the opposite is -9. That is my excluded value. So you can also just shortcut to that too. You don't have to say, oh, what makes this 0? Okay, the other instructions for this part, though, is they want us to simplify it. Okay, total simplifying means we also have to factor the top. Okay, and there's a k squared, and there's no greatest common factor anywhere up there, so we're going to have to do 2 parentheses for this. There's nothing in front of k squared, which means we can jump straight to the back, and we're wondering what can times to 36 but add to 13. We have lots of options that times to 36, but if our condition is it also has to add 13, there's just one right answer, and that's 4 and 9. That's the only pair that times to 36, but also add to 13. So they will be our 2 separate parentheses. We have k plus 4 and k plus 9. And on the bottom, we still have a k plus 9. There it is. And this is just like back on 7.1 where we were canceling things. Look, and that's just the k plus 4 on top. It's not on the bottom, it's on top. That is the simplified function. And you can still put it over 1 if you want to, but because it is on top, you don't have to. Now, for those of you saying, wait, can't we plug -9 in now and get an answer? Yeah, we could. But the problem is the original function doesn't allow it. In the original function, you would get a 0 on the bottom. You'd actually get a 0 on the top, too, but that's actually super important in calculus. But L'Hopital, anyway. You don't pronounce the H. Ignore that. Okay, much later in your life. But if the original function has an issue with a 0 on the bottom, that's still an excluded value. Okay, next up. Okay, that's a group on the bottom. See the minus sign? That's not a group on the top. Okay, that's just a 42 and an x, and they can cancel separately, individually, together, whatever. Okay, on the bottom, we are going to look for greatest common factor, and there actually is one at 14, and look, they both have an x. That's important. The variables, it is really important that you pull those out if they both have one. Okay? And that will leave behind x minus 5 if we pull out the 14. Okay? Okay, we're looking for excluded values, and we're looking at the variables in the denominator. We don't care about the top. The top is, bleh. just the denominator and just the variables. Okay, this outside x, what could make the outside 0? Well, 0. If you plug a 0 in, it'll kill off the 14 as 0, and that's it. In the back, though, that's a group, okay? And you have to, because there's addition and subtraction, a 0 won't turn the group into 0. A 0 will turn the group into -5. So you have to cancel the entire group. The front is easy. The front lone x's are always zeros for excluded values, but that guy, that's where you're pulling opposite for addition subtraction numbers. Okay? So our excluded values are 0 and 5. Okay, remember the excluded value over here at 0. That's a lone x at 0. It means something weird is happening in the graph. Okay? So this tells us that, you know, if you were to graph this, there'd be something weird going on at those two x locations. Okay? Now we're going to simplify the rest of it. That means we're going to forget about excluded values. We've already found them. And now we're just going to see if there's anything that can cancel and make this a simpler function. X minus 5, there's no other group, so he's stuck. But those lone x's, they cancel. They are now gone. And 42 and 14 actually do reduce each other. Okay, the 42 reduces to a 3 and 14 reduces to a 1. 14 happens to go into both of them. Okay, so there's a 3 that remains on top. The x on top canceled. And then on the bottom, there's that 1 on the outside. A lot of people will hide that 1, but just so you know that it's there, it is there. Okay, and the group x minus 5. And again, most people are going to hide that 1, and so the only thing on the bottom is the x minus 5. So you've got excluded values, and you've got a simplified function. Remember, these excluded values, if you plug in that 0, it doesn't look like an excluded value anymore. In fact, it looks like it would turn into 3 over -5. But if you go back to the original and plug in a 0, the whole bottom is going to go to 0, and that's where graphs basically explode, the universe implodes, collapses in on itself, and people give you dirty looks for doing that. So just don't destroy the universe. All right, first of all, we're going to look at the denominator and all the variables in the denominator. Only the variables. This guy doesn't have any variables. That means there are no excluded values. If he doesn't have variables, he doesn't have excluded values. The variables, plugging things in for x, it's a domain, okay? The variables are what are making the excluded values. If that had been just a 14 out in front of the parentheses, we wouldn't have 0 as an excluded value. So this 15 doesn't make an excluded value, okay? Next up, we're going to simplify. So we're going to look at the top, and is there a greatest common factor? Well, 15 sure looks like a greatest common factor. I think it can go into everybody up there. That gives us r plus 1. We're going to cancel out the 15s, and there's our simplified function. Again, because it's a top, it's a numerator amount, you can kill off the fraction. If that had been in the denominator, we would need it to be underneath a 1 that isn't hidden anymore. That is how you find excluded values. Okay, we are now on to discontinuities. Funny thing about discontinuities, they are basically the same thing as excluded values. Okay, so if it is asking on your worksheet to find excluded values, okay, it's asking you to find discontinuities. The reason there's two names, though, is excluded values are kind of trying to steer you to thinking about domain. Okay, discontinuities are steering you to think about what does that look like on a graph. Okay, so just to kind of give you a definition here, a discontinuity, it is an excluded value. Okay, and you actually find them the same way. So we're going to be repeating what we did in the first part. But the reason it has this different name is because what it's doing is it's describing places where the graph is not continuous, okay? It's describing places where if you were tracing a graph with your pencil, you'd have to pick your pencil up because the line stopped, because it was not a continuing line. It was not continuous, okay? It was, in fact, a discontinuity or discontinuous. So we have a rational function, and this is the graph that that rational function makes. And so if we trace it, all of a sudden there's this little hole here. That's kind of weird. Okay, that's a break in the graph. Okay, you can't trace over the hole because your pencil would fall in the hole and get stuck. You would have to step over it somehow and continue on the other side. So there's a break in the graph. It's a discontinuity. Now there's another break in the graph right here. Okay, the dotted line, okay, and it continues on to the other side, and you can't trace from one side to the other. The dotted line is symbolizing where the break is. The dotted line is actually not part of the graph itself. Okay, so as you find discontinuities, we're going to find them the same way as the excluded values, but for discontinuities, they're describing holes or asymptotes. Okay, there's two kinds. We're going to talk about the kinds in a minute. Right now, though, we're going to focus on finding discontinuities. Okay, so if your instructions are to find discontinuities, you find them the exact same way that you find excluded values because that's what they are. Okay, so on the bottom, there's a squared, and it's not going to come out with the greatest common factor, which means 2 parentheses. Now, this happens to be a difference of squares. These are the conjugates, where you go +1 - 1, and because they're conjugates, you can just hit the front and the back, and the middle is going to cancel. Okay? All right, so we've simplified the denominator, and now we're going to look at all the variables in it to find our discontinuities, or our excluded values. This guy will produce a -1. That's where that group goes to 0, and the back group, +1. And if you look at the graph, at -1, there's a discontinuity. Okay, and at +1, there's that very big break in the graph. Okay, those are discontinuities. They make the graph discontinuous. They are also excluded values. Okay. Now, the top, we could factor the top. In fact, we will in a minute. But right now, let's just keep playing with discontinuities, okay? So we're going to keep finding them just so we get that straight in our heads, how you find them. And then we'll start classifying them. So in the bottom here, we do have an x squared, but there's an x on both terms. That makes it a greatest common factor. We can pull it out. And when we pull out the x, that will leave behind x + 8. Okay? We're going to find the discontinuity, so look for the variables. There's a variable out here. He's a loner. Loners are the easy ones. That's just 0. Okay? The groups, that's where you have to cancel the entire group. So +8, what could cancel that? A -8. Okay? And those, and remember, you look at your variables, okay? So those are the discontinuities. They are also the excluded values, okay? They fulfill both rows. And at those points, if that was to be graphed, we don't have a graph of it, but if we were going to graph it, at 0 on the x and -8 on the x, something weird would happen to the graph. Okay, last one. It's a trinomial with an x squared, and that x squared is not going to come out on a greatest common factor. In fact, there are no greatest common factors. But because the front is clear, we can split it into x and x, and all we have to do is worry about splitting up the back so it subtracts to 10. So we need factors of 24 that can subtract to 10. So let's make our factor list. So we've got 1 and 24. We've got 2 and 12, There's 3 and 8, there's 4 and 6. Now you got to be careful with the operation here because we're subtracting. It would be really easy to say, oh, 4 and 6, they make 10. And you're right, they do. But they make it by adding. We need to make it by subtracting. So we're actually going to go with 2 and 12. So we have an x with a 2 in its parenthesis, and a 12 goes into the other parenthesis. Now 2 times 12 is 24, but we want negative 24, so somebody's negative. So the question is, how do we combine them to make a negative 10? Who gets to have the negative? Probably the big guy if we're going to make a negative middle number. So we have 2 times negative 12, that's a negative 24. And then combining like terms, 2 and negative 12 combine for a negative 10. Okay, that's where the middle term is coming from. So we're going to find our discontinuities. Again, we're looking at just the x's. If there are random numbers outside the parentheses, if they don't have an x, they don't count. So this group, what could cancel it to 0? A negative 2. Back group, what could cancel that to 0? A 12. Those are the discontinuities. Something messed up at those two numbers is happening on the graph. A giant hole, a giant canyon, something weird. But yeah, those are the discontinuities. Okay, last but certainly not least, we're going to talk about the kinds of discontinuities that you might run into. There's two kinds, holes and vertical asymptotes. They're kind of self-explanatory. The hole is pretty much what it looks like. It's a hole. That's a hole. Okay, you could be walking along, and as long as you placed your feet correctly, you could step over the hole. So if you were driving your car and it was a pothole, as long as you hit like the edge, or if there was a little pothole, you might not even notice. Okay, that's a hole. We're going to put a slightly more formal definition on it. We're going to call it a removable discontinuity. You can kind of think of it though, if it's removable, you could step over it. Okay, or your car could drive over it and you might not even notice. It might just be a little dent in the pavement and you might not even notice if you were driving. Okay, so you can step over it, and as long as you were careful and you didn't like fall into it, you could kind of ignore it. So this is what you saw on Desmos when it wasn't this big canyon going to infinity, but you were dragging the dots around and they just disappeared. Like it was gone, and the y value was NaN, or not a number. Okay, that's Desmos's way of saying, well, this is undefined and no solution, and we can't have this here. This is not allowed. Okay, that's a hole. Okay, so you drive along, you step over it, yeah, you can remove it. Not really going to impact your day. Okay, vertical asymptotes cannot be removed. If we keep with the driving analogy, you can drive over a pothole if it's not too big, and you may not notice it. But, for example, if you drove over the Snake River Canyon, you would notice. I don't recommend that, by the way. I stick to the Prime Bridge. But if you just drove your car and tried to hit the other side of the canyon, Evel Knievel tried it kind of unsuccessfully, that's a canyon. Okay? You can't, even if you took it away, the dotted line, you couldn't get from one side to the other side because one side's down at negative infinity and the other side's up at positive infinity. You can't even connect them. Okay? So it's like a big canyon. The lines can approach it on either side, but they can't actually touch it. Okay? And again, if you were to drive your car into the Snake River Canyon, it would impact your day. You would definitely notice that. Okay? For the few seconds you were alive to notice it. Again, don't do that. The potholes, they might bend the rim, but that's easier to take care of. Okay, so how do you tell, because this negative one is a hole, and the positive one is definitely not a hole, that's a canyon, that's an asymptote. How do you tell which one is which? And it comes down to the fact that things can sometimes be removed or canceled from these rational functions, okay? If it's removable, another way of thinking about that is it's cancelable. We're just going to say it can cancel because I'm not going to try to spell cancelable. I don't even know if that's a word. Okay? A removable discontinuity can be canceled. So we're going to factor this sum of cubes. We haven't done this for a few units, so we're going to try and jog some memories here because these are going to start showing up a little bit. So remember, there's the acronym SOAP. SOAP, it's something that middle schoolers really need a lot of. Okay, so S is for same, O is for opposite, A and P form a phrase, always positive. Okay, by the way, high schoolers and adults should use SOAP as well. Okay, and these are how you figure out what the signs are. So same sign, then O and always positive are in the second parenthesis, O opposite, and then always positive is kind of self-explanatory. Okay, the first parenthesis, the little one, everybody goes down to their roots. So you want the cube roots of these perfect cubes. 1 happens to be its own root because 1 is a weird number. All right, in the second parenthesis, front times front has to get us back to x cubed. So we've got x times, this is going to have to be x squared. Okay. 1 times the back has to get us back to 1, so this is going to be 1 technically squared, and 1 squared is itself because it's its own root and all of its own powers. The middle, where it's opposite, is what's doing all the canceling. Okay, kind of like conjugates cancel all of their middle parts. Okay, the middle of the longer parentheses is canceling. So it has to be made of both 1 and x. So you just times them together and you get 1x. Okay, and that's how you factor cubes. Sums and differences both can be factored with SOAP. All right, we're now looking for what can cancel. Well, look, there's parentheses x plus 1s. They can cancel. And the x plus 1 on the bottom was making a discontinuity. All right, because the parenthesis it came from canceled, that discontinuity is a whole because it was removed out of the rational function. Okay, x minus 1 does not cancel. When you factor cubes, the trinomial you make cannot be factored, at least not happily. You'd have to pull out quadratic formula or completing the square. Okay, that's a vertical asymptote, which I am not going to write out. I'm going to start abbreviating it, and you are certainly welcome to abbreviate it as well. So if the group or the letter that makes the discontinuity can be removed, then it's a whole. Okay? So a whole is a discontinuity, also known as an excluded value. They're the same thing, okay? That cancels, okay? The place it came from canceled. That is a whole. Like you can pave a pothole, okay? You can fill it in with dirt. You can make it all better. The vertical asymptote, because there's other kinds of asymptotes. The vertical asymptote is a discontinuity, also an excluded value, that does not cancel. The group or the letter it came from doesn't cancel. Okay, so the thing that made it cannot be removed. It's like trying to pave the Snake River Canyon. That would be an impressive project. Don't pave the Snake River Canyon. Okay, so this -9, it came from something that canceled. It came from an x plus or a k plus 9 that canceled. That means it's a whole. It came from something that canceled. Okay, this outside x that made the 0 also ended up canceling. So that 0, there's a hole in the graph at 0. But the 5 did not cancel. Okay, its group stuck around until the end. So there's a hole at 0, and there's a big giant vertical asymptote canyon at 5. This one didn't have any excluded values, so we don't care. This guy, nothing is canceling that x. It sticks around. That is a vertical asymptote. Okay? So if the place it comes from sticks around, it's a vertical asymptote. If you can remove where it comes from by canceling, then it's a whole. So we're going to classify these guys. Those x's just canceled. So look at what came from that x. That was a 0, and it came from something that could be removed, that could be canceled. That's a whole. The negative 8 came from a group that didn't cancel. Okay, that group cannot cancel. So that negative 8 is a vertical asymptote. There's a vertical asymptote happening where x is negative 8. All right, last one. Here we go. We're going to find factors that times to 6. We want them to add to 5. Well, 6 and 1 will subtract to 5, but remember this time on the top we're adding. Okay, which means 2 and 3 are probably what we're going to go with. Okay, all the excluded values have come from the bottom. What the top does is it tells us what kind of excluded value they are. Are they a whole? Are they a vertical asymptote? Okay, the x plus 2 group canceled, but this 12 did not. That's a vertical asymptote. You cannot get rid of it. But a whole, you can fill in a hole. You can remove a hole. Okay, that's the thing Desmos falls into. So that, the negative 2, that's the hole.